Alright guys, welcome. In this video, I'm going to pick up with some multivariable calculus, and we're going to be evaluating triple integrals today. So I did a video the other day, not yesterday, but the other day on double integrals. We went through and evaluated some double integrals. And I talked a little bit about how to go about evaluating those. And we're going to start with triple integrals today. I said I was going to do triple integrals, so I'm going to do them today. So the hardest part of evaluating, the hardest part of double integrals and triple integrals in general, I think most would agree with me, is actually setting these up. Very rarely are you just going to be given some double integral or triple integral that's actually set up for you. We call those iterated triple integrals or iterated double integrals. The limits are already defined and you don't have to set them up. You just have to go through and evaluate them. The vast majority of the double integral and triple integral problems you will encounter in multivariable calculus, you're going to actually have to set them up on your own. And to me, that's the hardest part of the whole thing, is actually setting them up, because how you set them up depends on the region that you're integrating over, especially when it comes to triple integrals. And sometimes you need to start off with just a sketch of the region before you can even set them up. And some order integrals, double and triple integrals, require a change of variables and change of the order of integration. So actually setting them up is not, it's actually the most difficult part of evaluating them. Very rarely for the double and triple integrals themselves are they going to be extremely difficult. Sure, they can have some methods like use substitution, all that kind of stuff that may need to be applied. But for the vast majority of the integrals, actually, when the triple integrals or the double integrals, when you actually get them set up, you actually realize they don't require really any of those techniques that we talked about before. They're very simple to evaluate, and they're not hard at all to evaluate. The most of the work that goes with these double and triple integrals comes from actually setting the problems up, not actually evaluating the integrals. But there are some cases where you'll just be given some and you're just asked to evaluate them. And we're going to do about 4 examples here. Again, these examples are relatively easy. They're not very difficult at all, in my opinion. We're going to go through how to deal with them. Pretty straightforward process, very similar to what we did with the doubles in the other video. So that's just a general introduction into just a little bit about double and triple integrals. Again, I don't primarily stream from Facebook, so if you want to see my videos on really anything, I primarily stream from Instagram. That's where all my math content is going to be. So check out Instagram to see constant updated content. So we'll start with number 1. So you have this triple integral here. We're going to start with this one. Also, make sure you have your calculator just in case you need it. Shouldn't need it too much in the examples that I picked, but just make sure you have one. All right, so you got this triple integral. So it's going to be from 1 to e, from 1 to 2, from -2 to 2. And we got xy squared over z, dz, dx, dy. So with the triple integrals, it's basically 6 possible orders of integration. It could be dz, dx, dy like we have here. It could be dy, dx, dz. It could be dx, dy, dz. It's 6 possible orders of integration. Also, keep in mind that for the triple integrals and double integrals as well, your limits of integration don't have to be constants. They don't have to be just some regular number like 2, 4, 5, 6, whatever. There are cases where it'll be an expression. It could be square root of x squared plus 7 or something like that. It doesn't have to be some constant value for your limits of integration. So don't be surprised if you see a limit of integration that is not a constant value. It doesn't have to be, but you approach it the exact same way you approach integration in general. You don't change the process regardless of what the limits are. You apply the same process. So much like for the double integrals, the triple integrals, how we start depends on what we're integrating with respect to first. In this case, we're integrating with respect to z first. So much like for the double integrals, we treat the other variables, think of it kind of like a partial derivative. We treat the other 2 variables as constants to start with. And much like for the double integrals, we work our way from the innermost integral to the outermost one. So double integration and triple integration is not hard to pick up on at all. Obviously, you need to make sure that you are pretty good with the integration process, and then you should be fine. But it's not hard to pick up on how to evaluate double and triple integrals at all. It's actually not that bad. So I know that we're going to be treating the other variables as constants, but I'll always start out by writing everything out just so you can kind of see what should be done first. So since we're integrating with respect to z first, that means we're treating the other two variables, x and y, as constants, which means that you can take them out, and I highly recommend removing them. So you'll take out the x, you'll take out the y squared, not just y squared. And what that means is you'll just simply be left with 1 over z dz in the integrand, and that's going to be evaluated from 1 to e. Okay? So now we integrate. So the xy squared, that carries over. What's the antiderivative of 1 over z dz? That's just ln of z, or ln absolute value of z, but we'll get rid of absolute value because we have some limits. And you're just going to plug those in. So it's going to be from 1 to e. Now remember, ln of e is just 1. And remember, ln of 1 is 0. So we just get 1 here. If we multiply xy squared by 1, we just get xy squared. So now we move to the second most integral now. And this one's going to be from 1 to 2. And here we got xy squared. And this time we're now integrating with respect to x. So again, since we're integrating with respect to x, we got a y squared in here. You can just remove it. It is a constant, or we're treating it as a constant. And what's left is just x and dx in our integrand evaluated from 1 to 2. The process continues, and we get y squared, x squared over 2, and we'll evaluate that from 1 to 2. So if you saw the video that I did on double integrals the other day, you can see that the process is really not that different. It's actually not different at all what we were doing when we were evaluating those iterated double integrals, the ones that were already set up for us. The process is very simple and very similar. It's actually the exact same. The only thing that's different is we just added an extra integral. That's all. And if you look, at least for this first example, so again, every triple integral or double integral is going to be easy to evaluate. But as you can see here, we're really not using any particular technique. We're not using any substitutions, no by parts, no trig substitution. Not that those methods can't be used with double and triple integrals. They certainly can for some of the more harder examples. But we're really not using anything complicated here. We're using some basic first semester calculus understanding of what antiderivative, or just definite, or, well, starting about definite, or so calc 2. Just some basic calc 1 and calc 2 understanding of antiderivatives. So we sub in the upper limit first, so that's 2 squared over 2, which is just 2. Subbing in a 1 just gives us 1/2. So we got 2 minus 1/2, which is just 3/2. We then multiply that by y squared. And since 3 over 2 is a constant, we could just take that out. So we'll take out a 3 over 2. And we'll evaluate our last integral from -2 to +2. And then we just got y squared dy on the inside there. And we go about the process very similar to what we did for the first two. So this 3 over 2 is just a constant. Just applying the constant multiple rule, this becomes y cubed over 3. Again, evaluated from -2 to +2. So if we sub in the upper limit first, we get a positive 8 over 3. We subtract that from a negative 8 over 3, which obviously changes this to 3 over 2 multiplied by 8 over 3 plus 8 over 3, since it is two negatives. So this obviously gives us 3 over 2 multiplied by 16 over 3. Remember, 16 times 3 is 48. 3 times 2, or 2 times 3 is 6. 48 divided by 6 is just 8. So that's actually the answer for this triple integral. So the final answer here is just 8. So as you can see, for this first example, again, all triple integrals and double integrals are not the same. So just because this one was a relatively simple one doesn't mean that they all will be easy. And I have, again, I don't primarily stream from Facebook, so I don't really have any math content at all on Facebook. Well, I do, but from, videos from possibly a year or maybe 2 years ago, whatever. But the vast majority of the math content is on my Instagram page. So We certainly have examples on my Facebook page of more complicated examples of evaluating triple integrals. Also, we actually set them up, evaluating triple integrals in spherical coordinates, changing the order of integration, which requires sometimes a sketch of the region. I got all of those advanced topics on my Instagram page and not really on my Facebook page. So all we're doing is just evaluating them today. Again, all triple integrals are not the same, so just because this one was a relatively straightforward one don't mean they all will be. But again, what you'll find when you take multivariable calculus, setting them up is actually the most difficult part because it has to be done painstakingly, especially because it depends on the region that you're integrating over, and oftentimes you can't set these triple integrals up at all without a good sketch of the region, which will oftentimes be given to you, and then you just got to set it up. Sometimes you have to sketch the region on your own. And then when you set them up, quite frankly, you'll find that just some basic Calc 1, Calc 2 integration skills is all that's really needed to evaluate most of them. So that was number one. We're going to take a look at another one. Again, these are very simple, basic examples of triple integrals, very, very basic examples of them. Most of them, quite frankly, will be like this. And they're very basic. We're not really using any advanced techniques here, by parts, use substitution, all that kind of stuff. We're not really doing any of that here. We're just evaluating them. So I also posted some pictures of the solutions as well, just in case you don't want to look at the video. Maybe you just want to see the solutions. So I'm going to kind of tilt the paper just a little bit. That way, these are the previous, these are the papers here that I have for the other videos that we're going to do. Those are all the problems that I've created that I want us to run through in other videos, so we'll run through those. All right, let's do number 2. All right, well, so we have this next one here. So this one, again, the limits of integration do not have to be constant values, don't have to be 6, 7, 8, it could be anything. So we got y squared to 4, from 0 to 4, or rather I should read them from outermost to innermost. So we got the triple integral from 0 to 2, from 0 to 4, from y squared to 4, with the square root of x, dz, dx, dy. So a different order of integration here. Actually, no, it's the same. No, it was actually the same order of integration that we have for number 1, but they can be different. It doesn't have to be dx, dz, dx, dy. It can be, it's 6 possible orders for the triple integrals. So we approach this no different than how we approached the last one. Okay, so in this particular case, again, we start from the innermost, and we got y squared to 4. We got the square root of x, and we're integrating this with respect to z first. So are we integrating this with respect to z? Yes, we are. And the square root of x, obviously, we're treating that as a constant. But you can't just take out this square root of x, although we're integrating it with respect to z, because, again, we're treating it as a constant. And since we don't have any z's in here, when we integrate this with respect to z, we just simply get the square root of x, but this time we just multiply it by z. And then you just evaluate it from y squared to positive 4. And you basically go about the process of subbing it in like you would any other time. So we have the square root of x multiplied by 4, and then it'll be minus the square root of x multiplied by y squared. So effectively moving to our innermost integral now, it's going to be from 0 to 4. And this time, we switch it up a little bit. Remember, multiplication is commutative. So we got 4 times the square root of x minus the square root of x times y squared. And all of this is being integrated with respect to x now. So you can break this up using the difference rule for integrals. So this would be the integral from 0 to 4. We got 4 multiplied by the square root of x dx minus the integral from 0 to 4 and the square root of x multiplied by y squared dx. And you can kind of break these up. Again, this is a long way to do it. The way I'm doing it in here. When you get the triple integrals and stuff in multivariable calculus, you'll actually go through these quite quickly, and won't have to do all these extra steps. The extra steps that I'm doing in the video are strictly for purposes of the video. So let's just deal with the first one. So again, if we're integrating from 0 to 4, 4 times the square root of x dx, well, the 4 can come outside. Actually, I'll do it like this, so from 0 to 4, we got 4 times the square root of x dx. So 4 comes outside. Remember, this antiderivative of the square root of x, this is 2 over 3 x raised to the 3 over 2. And we just evaluate that from 0 to 4. And people always ask me, well, how do I know that the square root of x dx, the antiderivative of that, is 2 over 3 x raised to the 3 over 2? And I always tell people that, remember, the square root of x can simply be rewritten as x raised to the 1/2. So you could essentially, of course, removing the 4 in this case, but just think about it without the 4 there. The square root of x can be written as x raised to the 1/2. You apply the power rule, you should end up there. So that's where, how I know. And that's just kind of something that you remember the antiderivative for. It's kind of like, what's the antiderivative of 1 over x dx? You know, you kind of remember that that's the natural logarithm. And so you kind of memorize antiderivative for some of the basic, just some basic integrals, basically. And so we sub in the upper limit first, simply due to the fact that I don't got enough room over there. Let me just kind of rewrite a little bit over here. So again, not doing anything that's really complicated that we haven't done before. So we know if we sub in the 4, we'll get 16 over 3. Sub in the 0 just gives us 0. So you get 16 over 3. And now we take the 4 and we'll multiply it by 16 over 3. Remember, 4 times 16, that's 64. 64 over 3 is what we have when we multiply by the 4. Let me get my other pen. Give me 1 second. I want to use annotate where we're at. Since I'm doing it in small little steps like this, it would probably be better to kind of give you a gist for actually what's going on. So 16 over 3, we just get that when we take care of the first part. Again, this is the long way to do it. You won't need to break it up into small steps like this. Once you start learning this stuff, you should be pretty good with integration, and you don't have to do it in small little steps like this. I'm just breaking it up a little bit for people that may not know. Same thing here. The y squared can be taken out, so we got 2 over 3 x raised to 3 over 2. We already know that's the antiderivative for that. And same thing here. It's just going to be from 0 to 4. And we already know what we're going to get. We're going to get 16 over 3 minus 0, which is just 16 over 3. Multiplying that by y squared, we get 16y squared minus 3. So we get 16y squared minus, divided by 3, not minus 3, but divided by 3. And so now what we have to integrate with respect to our last variable would just simply be that constant minus 16y squared over 3. So now for the last integral, this would be from 0 to 2, and we got 64 over 3. And we're going to be subtracting that from 16y squared over 3, and all of that has to be integrated with respect to y, which is the last variable here. And again, you can apply the difference rule for integrals. Again, you don't have to do it in small little incremental steps the way that I'm doing it, just for the purpose of the video. And I'm just breaking it up so you guys can see what's actually going on and actually see that it's not that much different from what we do with double integrals. Now, it should be easy to tell what the answer is going to be for the first two based on what we know already. So again, remember 64 over 3, we're integrating with respect to y. That's just a constant that we're integrating with respect to y, evaluating it from 0 to 2. So this is just 64 over 3 multiplied by y, evaluated from 0 to 2. Okay. Well, if we sub into 2, we'll get 128 over 3 because 64 times 2 is 128. Subbing into 0 just gives us 0, so you got 128 over 3. That's actually what we get for the first one when we break it up using the difference rule. And then this other one here should be easy to tell what the answer is going to be because we pretty much have an inclination of what the answer is going to be for this second one here based on the work that we did previously. We had 16y squared over 3, and we're integrating all of that with respect to y. So if we're integrating the constant from 0 to 2, 64 over 3 with respect to y, we got 128 over 3. Only thing we're doing here is we still have our constant 16 over 3, but we have a y squared. So obviously that would be 16 over 3, y cubed over 3 evaluated from 0 to 2. But again, we already know that when we sub in the 2, which is the upper limit, we'll get 2 cubed, which you know is 8 over 3, which we can leave alone. Subbing into 0 just gives us 0. So actually, I guess I can just go ahead and work it out for you. I'll try to kind of explain it to you without having to do a whole bunch of writing, but I guess since I'm doing the writing anyway, I guess I'll go through it. So we know we get 8 over 3, subbing into 0 just gives us 0. So we get 8 over 3. Now we got 16 over 3 multiplied by 8 over 3. Again, we're just going to get 128 over 3. 128 over 9, excuse me. 3 times 3 is 9. Sorry about that. And so essentially all we have at this point is just going to be 128 over 3 minus 128 over 9. So 128 over 3 minus 128 over 9. So long, drawn out way of doing it. Again, you need common denominator to subtract fractions. The good news is, which means you would have to find LCM. The good news is we know that 3 times 3 is 9, so we could easily get a common denominator there. But we'll just put in the calculator for the sake of time. And you'll be allowed to use a calculator for the sake of time. Small little calculations like that, you get 256 over 9. Small little calculation like that, your professor is not going to make you do small little calculations like that without a calculator. They'll give you a calculator, allow you to do the small little calculations and stuff like that. Could be done on your calculator because you're going to be busy doing all of the calculus stuff anyway, which would take up the vast majority of your time. So they're not going to force you to do all those small little calculations, stuff like that without a calculator. Or at least I would hope they wouldn't. All right, so the integral that we had here was from 0 to 2, was from 0 to 4, and then from y squared to 4. And we had the square root of x, and it was dz dx dy. So the answer here was just 256 over 9. That's the answer for that one. That's the answer for number 2. And I know it's a waste of paper, but I have plenty of paper, so no big deal. That's the answer to number 2. All right, let's move to number 3. So as you can see, well, maybe that one was a little bit more involved. But as you can see, for the examples that we're working on, they're not too difficult at all. Again, it's not going to always be this easy, but I got some extra paper just so we need it. All right, so what about this one? All right, so again, this one looks extremely difficult. The limits of integration are rather odd. Again, they don't have to be constant values. So we got the triple integral from 0 to 1, from 0 to the square root of 1 minus x squared, from 0 to the square root of 1 minus x squared. dz dy dx, again, another, well, actually this time it's a little different because we're integrating respect to x last. For the last couple examples, we was integrating respect to y last. But again, there's 6 possible orders for these triple integrals. All right, so same thing here. We're not going to approach this any different than how we approached the last couple examples. So it's going to be from 0 to the square root of 1 minus x squared. And you'll actually find that this one looks very intimidating, but it's actually very, very easy. So we're integrating with respect to z first. So that means we just get z, and that's evaluated from 0 to the square root of 1 minus x squared. So you're just going to be integrating 1 minus x squared minus 0, which you know is just the square root of 1 minus x squared. So now, for our innermost integral now, we have the integral from 0 to the square root of 1 minus x squared, and we're integrating the square root of 1 minus x squared, and we're integrating this time with respect to y. So hopefully you're seeing that this one is actually very easy. Since we're integrating this with respect to y, we're treating the variable x as a constant, so that means that we'll have the square root of 1 minus x squared multiplied by y, evaluated from 0 to the square root of 1 minus x squared. 1 minus x squared times 1 minus x squared is just what's under the square root, which is 1 minus x squared. So the square root of 1 minus x squared times the square root of 1 minus x squared is just 1 minus x squared, which is what's under the square root. So it's 1 minus x squared. Subbing in 0 just gives us 0. So effectively, we just end up with 1 minus x squared. And now we're on to our last one. So from 0 to 1, we're integrating 1 minus x squared, all with respect to x, which can, if we apply the difference rule for integrals, we get from 0 to 1, we're integrating 1 dx minus the integral from 0 to 1 x squared dx. So evaluating that, we just get 1. Evaluating this, we get 1/3. So essentially, we got 1 minus 1 over 3, which we know is just positive 2 over 3. So that's the answer for this triple integral. So this one looked extremely difficult. If you first look at it, it looked very hard to do, but it actually was very, very easy. So from 0 to 1, from 0 to the square root of 1 minus x squared. And again, most triple integrals will look this way. They will look absolutely impossible to do in terms of actually evaluating them. But once you actually start the process, you actually realize that not that difficult at all, despite how they may look. So the answer for this is just 2 over 3. So again, I know it looked very intimidating when we started it, but it wasn't that bad at all. This is 2 over 3 for that one. All right, so that was number 3, and we got one more. Again, I'll post the pictures of the solutions. And as you can see, we're actually running through this video a lot quicker than we ran through the one we did with double integrals, although those weren't too difficult at all either. All right, so this is our last example for this video. And by the way, if you have questions about this stuff, you can always ask. Don't be afraid. All right, so our last triple integral here, again, it's going to be from 0 to 2, from 1 to 2, from 0 to 1. We got y, z, e to the x, dx, dz, dy. So again, another order here. Well, we approach it no different than we approached the last couple. So again, since we're integrating with respect to x first, we're treating the other variables as constants. So I'm going to go ahead and remove the y times z, or the yz. And we know we're going to start with the innermost integral, and we just have e to the x dx that we're dealing with. So we get yz. We know the antiderivative exponential e to the x just itself, which is e to the x, technically plus c, but in this case, we got a definite integral. Then it's going to be from 0 to 1. So e to the 1 is just e to the 0 is 1. So we'll get e minus 1 multiplied by yz. So our second integral now is going to be from 1 to 2. And we got yz multiplied by e minus 1. And that's all going to be integrated with respect to z. Since I'm integrating with respect to z, the y and the e minus 1, which is just a number, if you plug it in your calculator, can be taken out. And it's going to be from 1 to 2. And on the inside, we can just leave the z in there, since we're integrating with respect to z anyway. So then we just end up with y multiplied by e minus 1. This becomes z squared over 2, evaluated from 1 to 2. So we get 2 minus 1/2, which we know is 2 over 3, or excuse me, 3 over 2. And then we just multiply y times e minus 1, multiplied by that 3 over 2. 3 over 2 is a constant. And since we're integrating with respect to y last, the e minus 1, which again is just a number if you put in your calculator, can also be removed. So we'll have 3 over 2 multiplied by e minus 1, which is just a constant. And then since we're integrating with respect to y last, and this would be from 0 to 2, we can leave the y in there. You can multiply the constants together out there if you want to. So this will give you 3 times e minus 1 all divided by 2. Applying the power rule, we get y squared over 2. And it's evaluated from 0 to 2. It's much easier when the lower limit, of course, is 0, because we know we sub in 0. Depending on what the integrand is, obviously. But depending on what your antiderivative is, you're going to get a 0 out in most cases. But subbing in the 2, and then we sub in the 0 after that. So we obviously get 2 minus 0, which is just 2. So then we'll just take the 3 multiplied by the e minus 1, which again is just a number. Divide that by 2, multiply that by 2. The 2's cancel out, just leaving us with the 3 multiplied by e minus 1. And that's actually your final answer. So the final answer for this triple integral is simply going to be from 0 to 2, from 1 to 2, from 0 to 1, whereas to integrate yz, e to the x, and it was integrated dx, dz, dy. The answer to this is just going to be 3 multiplied by e minus 1, which again is a decimal. You can put that in your calculator to figure out what that is, but it's just a number. And that's your answer for number 3. And so that is how you evaluate some triple integrals. Again, we didn't do any U substitution, no by parts, no trig substitution, no partial fractions, nothing like that was done in any of these examples. Again, I hate to keep repeating myself, but the vast majority of the triple integrals that you're going to be getting will require really nothing more than just some basic calculus knowledge to get through. Most don't require any advanced techniques that are required for most single integrals at all. Obviously, there are some differences in every integral, but for the most part, which one am I missing? 3. Which one am I missing? Oh, no, this was number 3. Sorry. This was number 3. So I'll post pictures of these so you guys can see my answers to all of these. And if you got any questions about them, you can obviously ask. But that's triple integrals. So if you guys got questions, let me know. I'll see y'all next time.